Now that we introduced the row space, we are interested in working with the column space now. Suppose the question says, hey, find the basis for the column space of matrix A. What are we going to do in this method? We're going to write down the matrix A using its transpose and then apply elementary row operation to write this guy in row echelon form. Then you find some non-zero vectors. The transpose of those vectors are basically forming the basis for the column space. So as easy as that. Take a look. In previous example, we had that huge matrix. Now we write the transpose of that matrix to find the basis for the column space. So instead of working with A, you are working with the transpose of A. You're switching rows and columns. Now that you have the transpose of the matrix, you're going to apply elementary row operations to get to the row echelon form. The pivot is 1, so we don't have any issue there. We can multiply the first row by -3, add it to the second row, multiply the first row by -1, and add it to the third row, multiply the first row by -3, and add it to the last row, and continue the process. It becomes 1, 0, -3, 3, 2, the first non-zero vector, 0, 1, 9, -5, -6, the second non-zero vector, 0, 0, 1, -1, -1, the third non-zero vector, and you end up with a 0 row for the transpose. So this guy is basically the column of the original matrix A. This is the transpose, am I right? So let's see. Since you have 3 non-zero rows for the row echelon form for the transpose, if you write each one of these vectors in transpose form, you end up with 3 non-zero columns. So these 3 columns form a basis for the column space of matrix A.